So welcome everybody, and as I discussed during lecture, I am going to do just a small intro video here to your semester project. So let's start by looking at where this information I'm about to discuss with you is located in Canvas. So if you go to the modules and you go down to week 11, exam 2 and project files, that's where I'm going to be referencing. So the very first document here, the sample solutions, that's for exam 2. But for the project files, it starts with this second one here, and this is 263 Project 2018. I've already got that pulled open, so I'm going to go ahead and show you this. So this is a description of everything that's going to be required for the project. It gives you a description of what's going to happen. It says this consists of a console program, which that just means the standard program that we've been writing to standard output. So program to process bitmap images. Bitmap, that's just a type of computer file, right? We can also use PNG, other types of image files. It says it will prompt the user for a source file name and operation desired, read the file, report statistics, prompt for an output file name, and write the modified image to the output file. So at this point in the semester, you have not yet talked about structs, you have not yet talked about anything related to file input and output. So at this point, some of that is going to sound something that you haven't heard before, and that's true because you haven't. So the purpose of this is to let you know what's coming, and you know what lectures are coming and what information you're going to be getting, and so you're supposed to set yourself up for a plan on how you're going to get this accomplished, since you don't yet know the tools to make this happen. So you're going to fill those in as we go. And matter of fact, some of the labs that you do in Zybooks will be pieces of this that you're going to put together later. Okay, so you know the next few labs that you do starting in the next couple chapters, some of those will be pieces that you need to complete this. Okay, so you're not going to have to write the whole thing from scratch out of nowhere. Okay, so when it says reading a file in, if you've ever thought about how to modify or change a file, even if it's just a text file, you know, at the end of the day, you know, a bitmap image is still something that's just a bunch of ones and zeros in a file somewhere. No different than any other text file to some degree. So you're essentially storing the status of each pixel, right, with the RGB, and we'll talk about that here in a second. But anyway, what you're going to do is have the user enter a file name, the file will be opened, and then you can do one of these operations on it. Create the negative. So that's, you know, if you were to create the negative and then take the negative of that, you'd get the original back. The blue shift, green shift, red shift maximize each of those components, which, you know, you'll have to figure out what the RGB component is. Intensity scales all the colors of every pixel by a percentage factor between 0 and 1,000%. Stop at maximum intensity, right? 255. And then the last one is encrypt. So there's 1, 2, 3, 4, 5, 6 options here. Okay, and we haven't gotten into bitwise operations either, right? This is exclusive OR. So for now, okay, you're going to be coming up with a project plan that gives you a plan of attack for all of this. Okay, and there's some other things that you need to keep in mind when you're trying to figure out where to start. Okay, so as far as what is it supposed to do, there's actually an executable file that's available for you to run so you can see how it's supposed to operate. So this is a sample run that's just been printed onto the Word document that you have. Okay, so I'm actually going to run that file and show you how it's supposed to work shortly. So it says, do not use canned graphics libraries. The code must be written by you. Okay, so this is not a copy and paste operation. So it says several bitmap files are provided as test vehicles and a header file, RGB.h, defining the important bitmap constants and structs or structures. And the zipped copy of the program is provided as a demonstration of suggested behavior. So that stuff is located in these two zip files and this .h. So the imaging 2017.zip, if you unzip that and extract it, okay, So this is what is contained in there. There's a sample, all right, of this bitmap image. There's the executable, which if you were to build your program and send it to a file that could be opened without the environment that you code in, that creates an executable file, and that can be run independent. And then there's another one, a test that you can use as well. Okay, so that's all in this file. The bitmap samples, that's got more than just that buck there. So that's the one I copied in there. And so you could use any of these. It has to be 24-bit, and I'll talk about that here in a second, RGB. So any of these can be copied in there, and then you can see how it operates. So let's see how it operates. Come back into the imaging. I'm just going to use the buck.bump and the capital test.bump. Okay. So enter the bitmap file. Okay, so buck.bmp. And it doesn't matter which one of them that you use, they have to be in this test folder, right? Or the full path if not in the current directory. So when you're testing it, it's important that you paste into here, in this same folder that you're running this out of, because that's where it's trying to pull these files from. If it's anywhere else, you have to give the full path starting with C. Okay, so there it is, buck.bmp, and the output file, I'm going to use that capital test.bmp. Okay, so now it's loaded. It gives the size, it gives the height and the width and the bits per pixel, 24. So it says enter the first letter of operation desired, the negative, encrypt, intensity, red shift, green shift, blue shift. So I'm just going to do the negative, right? So remember, that was just typing in one of those first letters. So if I hit in, it says it wrote the test file, and here's the size. Okay, so now it's already ready for me to run this again. I'm going to go ahead and quit. Now look, you can see what happened to the test is it put the negative of that original bitmap file into this test. And so there's the negative. So you can see how it's supposed to operate. Okay, and you can play around with that and try the different, the encrypt, the blue shift, the red shift. But that's essentially what it's doing. Essentially, it's going in there and, at the pixel level, at the bit level, essentially, it's changing things around to make it appear a little bit different. Okay, so with that being said, let me go ahead and come back to here. All right, so that's how it's supposed to operate. So you might be thinking, where do I start? It says you will combine code already developed in labs exercises for several parts of the project, such as file I/O, struct access, dynamic memory allocation, bit fiddling, and error checking. So a lot of this, as I said, is going to be accomplished in the Zybooks. So where I would start, and before you even know how to do some of this stuff, it says create a quick and dirty demo of the code within the first week without all the functionality. Every time you change the code, make a backup copy with the date and the name there before changing it so that you can revert to working code if your change proves detrimental. So, this is how I would accomplish that. So it says create a quick and dirty demo of the code within the first week without all the functionality. When I see that, I think to myself, I just need to create function stubs. Now, you may or may not have remembered from chapter 6 what that means, but it's in your Zybook. So a function stub is a function definition whose statements have not yet been written. Typically what I will do is I'll put some printf statement in there that says this function has been called, just so I know that it's been called, but it doesn't actually do anything. Okay, so you can create, you know enough at this point to create the shell that says if the user enters this letter, choose this function. Okay, and then you call that function. It's just that right now it doesn't do anything. So like I said, I will put some printf statement in there that just says this function has been called, or something to that effect, just so I know when I'm testing through it that it's working, the functionality is working the way I expect it to. Okay, so this is starting to get into what we call modular development. So when you watch me do code, or you watch any professor do code in class that just comes up with something to program, that's essentially incremental development. It's a process in which a programmer writes, compiles, and tests a small amount of code, then writes, compiles, and tests a small amount more, an incremental amount, and so on. And so that's how I typically develop things for students at this level, right? So that means that I start off with, here's all my variable declarations, and here's my very first print statement, and then I compile it, make sure there's no errors, see how it appears on the screen, and kind of modify things as I go. And then I can always go back in and add other functionality later, but that's all an incremental process. Modular development is where you divide ahead of time everything into separate modules that can be individually tested, and then, you know, separately, kind of in a silo, and then at the end combined into a single program. So that's the way most, you know, software development works, right? You don't just have people that sit down and from scratch they just, you know, they write Windows incrementally, right? They divide it up between a lot of different test, you know, project groups and things like that, and each group is working on a specific piece of that, and then at the end they all combine together for the bigger single program. So you are going to be utilizing function stubs, and you're going to be somewhere in between here, because right now you have to think modularly because you don't know enough yet to just sit down and write it from scratch and just write a little bit here and a little bit there. You want to start off with this type of a development this time, where you've got everything divided into modules, and then you'll fill in those pieces as we go. Okay? So just wanted to point that out from the Zybooks. So coming back to our document, it says recommended steps in the successive refinement of your program. In other words, get your program to do just the steps 1 through whatever on several test files. So this should be the order in which you try to create this project, right? So, you know, the first thing is opening the file. The next part is allocating memory. So this is the order in which it's suggested that you construct this. Okay, now this part of it where you just create the demo with the function stubs, that's independent of this. Once you have that created, then start working on each piece of this, right? So one of the things I want to point out is this is an RGB, right? It's red, green, and blue. And so one of the questions that I had a long time ago, because if you know anything about the color chart, right, it's red, yellow, and blue that are the 3 primary colors, and every other color is based on some combination, taking one away, adding one more of the other for every color known to man. Okay, so here's a brief explanation about why we use RGB and not RYB. Okay, so this is from an article on medium.com by Austin Coding Academy. So the question is, if the primary colors of the wheel are red, yellow, and blue, why is web color measured in RGB? Red, green, blue, right? So that's important to somebody who's trying to program a microcontroller or trying to program a computer that's going to be hooked up to a monitor that the user is going to use. So RGB is what monitors use for colors, because monitors give off or emit light. So it says the distinction is that RGB is an additive color palette. The more you add to it, the brighter it gets. Add all together, you get white, the brightest. So a monitor gives off light, so that's why we use this combination. So you can just keep making them brighter and brighter and brighter, add them all together, and you get more of a lighter color until you ultimately get white. Okay? For RYB, so this, they're calling it CMYK, is what you would expect to see on a printed page, because pigment or color absorbs light. So it's a subtractive color palette. So if you add them all together, like you do with your crayons, you get black, right? Because they all absorb the light and there's nothing left to reflect. So it says the more colors you add, the darker it gets, because pigment on printed material absorbs light. So that's the difference, and that's why we use RGB as opposed to like an RYB situation. Okay, so here's what's due. In a week, you are to give me a project plan, and it's just one page, and date, your name, a description of the project as you understand it, and then a list of tasks and a schedule to get it done. Now, I'm not going to hold you to this schedule, but I want you to have this sort of laid out in front of you so that you can kind of give yourself a check. This isn't a full Gantt chart, right? This is just a recommended schedule for you to follow so that you don't fall behind. Because we have finals coming up, we have a lot of other things going on, you may have projects in other classes. This gives you something to reference that sees if you're fairly on track or not, okay? So just, for each part of this, give me your due date, and then what have you done for your initial research. I already did a little bit for you, by showing you some stuff in the Zybook textbook, and then also from that medium.com article. So that's just, you're going to want to dive into this a little bit more, okay? So I need this in a week of this posted, okay? Now, another one of the things that's included is this RGB.H, okay? So that is the header file that you're going to include in the source code that you write, and it needs to be inside the folder in which you're working out of, the project directory. So this is what it looks like, and essentially it's just defining a few things that you're going to be using, okay? You can see here that these are double words and these are words. This is how you can, if you look at these, you can determine, like the size and the width and the height. It gives you a place to store these, and then, be able to, at the bit level, change things, okay? So you can see here, we have this structure called, RGB triple named picks, and so we've got a few picks here, RGB and white, and so you can see inside of this document here, it goes on to explain, what the RGB is, okay, and it says bitmaps may be stored in a variety of formats. They may be compressed and may include a color table that converts 8 bits to 24. To simplify this exercise, we will only use 24-bit RGB true color bitmap files. So this says 24-bit RGB consists of one unsigned byte for each for red, green, and blue. So that means that you have 8 bits for the red, 8 bits for the green, 8 bits for the blue. That gives you the 24 bits. So it says a value of 255 in the red byte and 0 in the green and blue makes a very bright red pixel. So a value of 0 means no hint of that color component. So black is 000, white is 252525 because that is the maximum, right? If you have 8 bits, that's 256 counts, and that counts from 0 to 255. So that's what you have in each one of these places here is 1 byte. So it says grays have equal color intensities, RA equals G equals B, of less than 255. Okay? So, you can sort of play around with that too, and if you go to buy paint, it's going to have some other type of component, right? It usually has 3 values that make up your, house paint or whatever, in whatever shade that you got it in. So remember, this is not on a wall or on paper. This is emitting off of the screen. Okay? So it says bitmap files start out with a file header structure of a few bytes telling the file size and type, followed by a header telling features of the image. Okay? So it says it's confusing to remember whether the red or blue byte is the lowest 8 bits of a pixel, called RGB triple in Windows, or pix in our RGB.H header. So it says using C structs, you don't need to remember the byte order. The compiler takes care of that. If you have a pointer P pix, then the red component can be identified as P pointing to the R component. Okay, and so that's in this RGB setup here. So you have B, G, and R. So you have separate components that you can point to, and you don't have to remember whether the R is out front or the B is out front in your 3-byte number. Okay. All right. So again, a lot of this stuff is coming up. You can see here. Here's the array of a struct using pixels. This one has bitmap file input, bitmap file input output and image processing, and bitwise operation, right? So bitwise operation is all the logic functions like and, or, greater than, less than, not, XOR, XNOR, NAND, NOR, all that good stuff. So anyway, all of that stuff is going to be happening at, by the end of the semester. So you just need to plan on what's going to be coming up in the order in which you're going to do your program and how you're going to design it. Okay? So I think that's all I have to say about this. This, at the very, very end of this document, is also the RGBH file. So you have it here in the document, and then you also have it as a separate file right here. Okay? All right. Hope that helps, and good luck.